Alright, hello, this is Mrs. Nearing. We're going to go over some mixed reactions practice, and our goal is to write net ionic equations for a variety of reactions. So this first one right here, I've got a solution of silver nitrate, and the silver ion has a +1 charge, the nitrate ion has a -1 charge, so that means silver nitrate looks like this. I just need one of each. No subscripts needed. Potassium carbonate. Potassium is +1, carbonate is -2. So that means I need 2 potassiums for every 1 carbonate. It tells me it's a solution, so that means it is aqueous right there. And this looks like a double displacement reaction. So what you want to do is you want to refer back to your page 2, the reaction summary table, to look at the various reaction patterns to know. So if it's a compound plus a compound, that's a double displacement type pattern, and we know we either form a solid, water, or a gas. So what happens is your metals switch places with each other. So the potassium is now going to be with the nitrate, and the silver is going to pair up with the carbonate. Whenever you write out the formula of a compound, you always have to consider the charges of the ions. So I'm going to make a little note up here above. Potassium is a +1 ion, nitrate's -1, so no subscripts are needed. Over here we know silver is +1 and carbonate is -2. So I actually need a subscript right there. I need 2 silvers for every 1 carbonate. And then I want to balance it. So I've got 2 silvers over here and only 1 over here. So I'm going to put a 2 there. Now I need 2 nitrates on each side. And I've got 2 potassium, so I'm all set. And then I want to look at my states of matter. So I know any compound containing a nitrate is going to be soluble, so that's AQ. And then silver and carbonate, those are not on my list of soluble things, therefore they are insoluble. So it's going to look like that. And then I need to eliminate any spectator ions. So I'm going to write out the whole, this takes a while in this type, but I'm going to ionize all my aqueous things. So my aqueous ionic compound, how it really exists in solution is it is split up into ions. So it's important to recognize, like, what is actually happening in solution. So I got a bunch of ions over here, and then on the right, my potassium nitrate, it's actually going to ionize. They don't stay stuck together. And then I have silver carbonate as my solid. So I'm going to look for spectators. It looks like potassium's a spectator and nitrate's a spectator. So what I'm left with is 2 silver ions and 1 carbonate ion combining to make silver carbonate. So this is my net ionic equation right there. Notice I'm balanced for mass, so I've got 2 silvers on each side, 1 carbon, 3 oxygens, as well as charge. I've got 2 positives and 2 negatives on the left, so that adds up to 0. And on the right, it's 0. It's neutral. Okay, so next one, a piece of lithium metal. So lithium metal, it's a solid at room temperature. Nitrogen gas. Nitrogen is part of Hofbrinkel. If I write that off to the side real quick, Hofbrinkel. If an element is part of Hofbrinkel, that means it's diatomic when it's in its elemental form. So pure nitrogen is N2. Lithium's not part of Hofbrinkel, so it's just lithium. I've got element and an element. I want to look back at my reaction patterns. And if I have an element and an element, that looks like a combination reaction. So in a combination reaction, we just combine those 2 elements to form a compound. So when lithium and nitrogen get together, I got a metal and a nonmetal, so that's an ionic compound. And whenever I write the formula of an ionic compound, I need to consider the charges of the ions. So lithium, when it forms an ion, it makes a +1 ion. Nitrogen makes a -3 ion. So that means I need 3 lithiums for every 1 nitrogen. And then once I have figured this out, I'm going to then go back and like scratch out my work here. Okay. Because now that I have the right number of lithiums, my compound is neutral. So that has to have a charge of 0. And now I need to balance it. I need 2 nitrogens over here, and I need 6 lithiums over there. All right, my next one. I've got a piece of solid aluminum in with some silver nitrate. So if I try to look at my reaction patterns, I've got an element and a compound. So that looks like element plus compound. That looks like a single displacement. So what happens in a single displacement is it's kind of like a double displacement in that the metals switch places, but what's different is one of your metals will be in its elemental form. So when the silver and aluminum switch places, I'm going to end up with elemental silver, so like pure solid silver. And now the aluminum is going to take the place of silver, and it's going to combine with the nitrate. So whenever I make a compound, so again what happened here is the aluminum and the silver switch places. When you put together aluminum and nitrate to form a compound, I always have to consider the charges of your ions. So aluminum's a +3 ion, nitrate's -1. So I need 3 nitrates for every 1 aluminum. And now I'm going to have to put a 3 over here to balance out my nitrates. And then I also need a 3 over here to balance out my silvers. So now I'm all balanced. I got to figure out my states of matter. This is a nitrate compound. And I know there's water around because it says aqueous right over here. So, and nitrate compounds are soluble. So that tells me this is going to be an aqueous compound. And then this is the important step. Let me erase this real quick. Is you're going to say, okay, what happens in solution? So your aluminum stays just plain neutral aluminum. But this silver nitrate compound, this ionic compound, it's going to split apart into ions. So you make some silver ions and some nitrate ions. Okay, over here on the right, you've got just neutral silver. But then this ionic compound right here, it's going to split apart into ions, aluminum ions and nitrate ions. So the only way you're going to end up with an ion is if an ionic compound dissolves in water. So notice how this silver is neutral, but this aluminum is an ion, because this aluminum comes from an ionic compound. So now you want to look for spectators, things that do not change. In this case, your spectator is nitrate. And so your net ionic equation, let me write off to the side, is going to be a neutral aluminum with 3 silver ions and turning into 3 neutral silvers and an aluminum ion. So a note here, you don't have to write this out, but note what's happening, if you can split this up into half reactions, is your neutral aluminum is losing 3 electrons to become this ion, and then you have 3 silver ions, each taking an electron to form 3 silvers. So this is your redox half reactions here. It looks like aluminum is being oxidized and your silver is being reduced. And then let's look at one more here. So sodium carbonate is dissolved in water. When you hear that, you want to say, oh, dissolved in water. How do we write that? AQ. So if it's dissolved in water, what that means is just you're going to label it as aqueous. And you mix it with a solution of hydrochloric acid. So that's also aqueous. It's a solution. And then it looks like a double displacement. I got compound plus compound. So my cations are going to switch places. So my H is going to go with my CO3. And my Na is going to go with my Cl. And I have to think about charges. So hydrogen is +1, carbonate's -2. So I need 2 hydrogens for 1 carbonate. Sodium, this is +1, -1, so no subscripts needed there. Let's stop and balance this. We need a 2 there to balance my sodiums. I need a 2 here to balance my hydrogens. And then I want to look at states of matter. So NaCl, alkali metal compounds are soluble. H2CO3, when I stop and look at this, I should say, hey, wait, this is on my list of gas-forming reactions. So if I look back at my page 2 here, whoops, I'm looking at the wrong page. But if you look back at your page 2, your table of things to know, you will notice that H2CO3 will, in fact, decompose and turn into H2O and CO2. So this is the real reaction which happens. We don't make H2CO3, we make H2O and CO2. Then I got to go through and ionize all my aqueous things. Whew, and that will take a while. But you end up with, in the end, what really happens is you have 2 hydrogen ions combining with 1 carbonate ion, making H2O and CO2. Notice that the sodium ions and the chloride ions end up being spectators. It's really just the H's and the CO3s that combine. And if we want to do... Let's take a look at one more single displacement one. So if you look down here at this one, number 9, a piece of copper metal is added to a solution of silver nitrate. This is one that we probably have done in class. And so the metal and the non-metal are the metal and the metal are gonna switch places. You're gonna end up with neutral solid silver, and then the copper is gonna combine with the nitrate. And you might be wondering, how do I know the charge of copper, right? Because copper is a transition metal. We don't know what the charge is necessarily. So they would actually avoid this type of question on the AP test because it's a little ambiguous. But the copper most commonly will form a +2 ion charge. So for the purpose of this question, I'm assuming it makes a +2 ion. And so that means there's going to be 2 nitrates for every 1 copper. But if we were on a test, if you assumed it was a +1 charge instead, that would be fine too. They would probably accept more than one answer, or they would just avoid this situation entirely. So now I need 2 nitrates on each side. I need 2 silvers on each side. Nitrate compounds are soluble in water, so that's going to be AQ. So if I split this up and ionize my ionic compounds, this is what I end up with. And neutral silvers, and I got a copper ion and 2 nitrate ions. And notice how my nitrates cancel out. So what's left, this is my net ionic equation. So I've got, I should rewrite that to be pretty, but I've got a copper and 2 silver ions making 2 neutral silvers and 1 copper ion right there. And notice again, I'm balanced for both mass and charge. So I've got the same number of silvers on both sides, same number of coppers, and the charge on the left is +2, and the charge on the right is +2. All right. Thanks for listening.